Hello everyone, what's up guys? So welcome back to our statics adventure where things should not move. So in today's mission, we want to keep a particle in perfect balance. Yep, we're talking about equilibrium. So imagine you're hanging a painting on the wall with two strings. It's not wobbling, it's not falling, it just stays there, chilling, relaxing. That, my friend, is equilibrium. No forces trying to pull it left, right, up or down. Another way to look at the concept of equilibrium is by looking at this hook, which is connected with two tension cables. It looks stable for now, but if the combination of the forces from cable A and B resulted to some magnitude which is not a zero, guess what will happen? Bada boom! The hook will be detached from the assembly to follow the direction of the resultant force. That is usually considered as a failure in an engineering structure, where the whole system becomes unstable. We definitely do not want that to happen to any structure around us. So the key concept to stability is to ensure that the net force or total resultant force acting on an object is zero. Simple je kan? If the resultant force on this hook is zero, then the hook will stay exactly where it is. So we can say that the system is in equilibrium. If you break it into two-dimensional system, if the summation of forces in X is equivalent to zero, it means that there is no sliding left or right. If the summation of forces in Y is equivalent to zero, then it means that there is no floating or dropping. And if you have to consider the Z-axis, so when the summation of forces in Z is equals to zero, so the system is not going upward or downward. Combine all together, ta-da! You've got yourself a particle in equilibrium. Now, before we go solving things, we need to visualize all the forces acting on the body. In order to do that, we need to free up the body that we are studying. That's why it's called a free body diagram. Let's look at this system. Consider a man pulling a box with a string. First, you have to isolate the bodies that you are studying. We have the box, the string, and the man itself. When you have freed up the body, you can now redraw the forces acting on each body. First, we can consider the interconnection to another body. The box is connected to the string. At this point, there must be a reactive force complementing one another. One at the box and another one at the string. Remember, it is complementing one another. Next, the string is interconnected to the pulling man. So again, another reactive force complementing one another. The second type of force that can be considered for the study for the body is the weight of the object. In this case, there is a weight to be considered for the box and also for the man. Weight will always be represented as a downward force. As for the string, its weight can usually be ignored because relatively it's too small compared to all the other forces. The third type of force is the normal reaction force. Literally speaking, the normal force prevents objects from falling through the surface. So normal force is represented by a perpendicular line to the surface. Last but not least is the friction force. It will appear at the contact surface between two different objects, whereby it tries to resist the direction of motion. So if the man is pulling the box to the right direction, friction at the contact surface would be in the opposite direction. The same goes with the friction between the shoes of the box and also the floor. Okay, so in the next video, we are going to do some simple example on equilibrium of a 2D system. Okay, stay tuned.